about 15 seconds or so for others to join, and then we'll start the webinar. Okay, let's get started. So welcome to the May IPNSIG Academy webinar, part of our continuing series. And today we're going to have a presentation from Fangjing Lu, who is a doctoral candidate at the MIT Media Lab. And he's going to be talking about some projects that he's been working on. And I just want to remind people that this webinar will be video recorded, and that video recording will be available on the IP events page several days after today. And please, one final note, please use the Q&A button, which the default location is at the bottom of your screen and a little to the left of center screen, for any questions you may have, and those will be handled at the end. So we've known Fangjing for about 3 years. He gave a presentation to Vint and other members of IPNSIG, and we were so impressed that we asked him to do quarterly updates at our Thursday morning IPNSIG tag-up calls. And he's been very faithful at that. And we think the timing is very right for him to share with the whole membership, because one of his projects is going to launch to the surface of the moon next year. So take it away, Fangjing, and tell us all about what you've been working on.
Cool. Thank you, Mike. Let me share my screen. Okay, I can see the slides, and is my voice okay? My audio okay? Cool. Let's get started. Hi, everyone. My name is Fangjing. I'm a PhD student from MIT Media Lab. Sorry about that. There we go. My main research is about how to use low-cost movable and static wireless sensor node for future lunar explorations. So this is the structure of my presentation. I will introduce both the movable and wireless sensor node, both the movable and static wireless sensor node. And I will introduce 3 featured projects in this framework. One is called the AstroAnt. It's a miniature robot working on the outside surface of the spacecraft for in-orbit inspection sensing. And one of this AstroAnt robot will be deployed to the Lunar South Pole in the IM2 mission later this year or the beginning of next year. And another 2 projects are called the Lunar WSN and Hexens. These are both ballistically deployed wireless sensor nodes, which can collect simultaneous in-situ data from different positions on the lunar surface. So the first one, the AstroAnt, it's a miniature robotic swarm servicing on the outside surface of spacecraft, rovers, or landers. And this project actually is from a past project which is done by my group. The old project is called Movable, which is done by Atom. It's kind of tiny robot with magnetic wheels and with another pair of magnetic wheels to pinch the fabric in the middle. This robot can move on your clothing and build a on-body sensor network. And so we think that possible to extend the applications of this platform to the space and build on-body sensor networks for spacecraft, rovers, and landers. So this is how this project came. So I designed these 2 models of the AstroAnt robot. They both have magnetic wheels and make them capable of moving on ferromagnetic surfaces or fabric. Like a space station or satellite, they're also covered by a piece of fabric or flexible material like bedclothes or MLI. So we did 2 parabolic flights for these 2 models. The first parabolic flight is used to test the mobility of this design in microgravity environments on different material surfaces, like sandpapers, like rock surfaces, bedclothes, simulants, aluminum with the magnetic paint or steel. And they all showed very good mobility and obstacle overcoming capability in microgravity environment. And the second parabolic flight is mainly used to test the sensing capability of this design in microgravity environment. So I designed the second model of the AstroAnt. Is much bigger and more powerful. It can carry bigger and more sophisticated sensor payload. So like a single thermal pile can do contactless temperature measurement of the surface. And combined with tracking information of the AstroAnt robot, we can localize some abnormal, like overheating or overcooling spots on the surface. And it can carry a thermal camera, can capture a heat map of the surface. And it can also carry a visual camera, can stream video from the outside. And this is the one frame from the captured videos in the parabolic flight. And about 2 years ago, we got the opportunity to work with Lunar Outpost. And you see, they developed this lunar rover called MAP-1 rover, which will be carried by the in-situ machine IM2 lander and sent to the Lunar South Pole. And we got the opportunity to send one of the AstroAnt robots to the moon, carried by the MAP-1 rover. So this is the robot I designed. It's very, very tiny. It's less than 3 by 3 by 3 centimeter, and as big as an eraser. And on the bottom, there's a thermal pile sensor, can do contactless temperature measurement of the surface it's working on. So on the back of the bigger MAP-1 rover, there's this little aluminum garage called aluminum box, which we called garage. And in the AstroAnt robot is inside the garage before the deployment. So when it's ready to deploy the AstroAnt, the garage will open, and the AstroAnt robot will be driving out and move around on the top panel, only on the top panel of the MAP-1 rover, because the top one panel is the radiator of the MAP-1 rover's thermal system. So by collecting some temperature data from different positions, we also want to use the data to help with monitoring the performance of the MAP-1 rover's thermal system. And this is the detailed design of the AstroAnt robot. From top down, it's the contact connector. It's for charging the Ant robot when the garage is closed. There are 2 poker pins on the top of the garage to charge the robot. And the main control board for the controlling. And there's a little heater attached to the battery, which is used to keep the battery warm, and 2 stepper motors as actuators. And on the bottom is the thermal pile sensor module. And there's another PCB board mounted on the garage, you can see here, which we called central station. It is used to relay data between the AstroAnt robot and the rover. So it communicated with the AstroAnt robot through Bluetooth Low Energy and communicated with the rover computer through serial port. So it used to relay commands from the rover to the robot, and then relay data from the robot back to the rover and then back to the Earth. So here's the short video I took during one of the thermal vacuum tests, showed that it works in the TVAC chamber. Yeah, so I already finished the flight hardware. We already actually delivered the flight hardware to Lunar Outpost. Now we are just kind of waiting for the launch, and the launch will happen the end of this year or the beginning of next year. So another part is about static wireless sensor node for future lunar exploration. So here I want to introduce two projects. The first is called Lunar WSN. It's a wireless sensor node designed for in-situ lunar water detection. So currently, the main force for in-situ planetary exploration is still, a single high-cost rover or lander. And the rovers, they move extremely slowly to guarantee safe trips. And they can only take a serious single-point measurement, which is not that good for studying dynamic phenomena, because when studying dynamic phenomena, we want some simultaneous data from different positions to study how the phenomena change over a big area of interest. And also for the rover, they move slowly, so that means it will take a very long time for them to go to somewhere that we are interested. And landers, they don't have mobility, so they can only study the area around themselves. And also more importantly, none of them can work in hard to reach or dangerous areas like rock piles, which might cause damage to the rover and also definitely not good for the lander's landing. So I want to use this kind of idea, like use ballistically deployed wireless sensor node to expand the explorations of this traditional system to the hard to reach or dangerous area. A tiny sensor node that can be shoot out from a rover's lander to the area of interest. And many sensor nodes deployed can create a wide wireless sensor network and collect simultaneous data from different positions. So this platform, this design can realize fast deployment to an area of interest, which is far away, by leveraging the low gravity level on the moon and also the vacuum environment on the moon. And also many sensor nodes, this kind of hardware redundancy can reduce the chance of failure. And they can collect simultaneous in-situ data from different positions, which is good for studying dynamic phenomena. This is the Lunar WSN sensor node design. It's a little cubic shape sensor node, which looks like a CubeSat. It's an omnidirectional design, very light, less than 150 gram, and very small, 5 by 5 by 5 centimeter. So it's the omnidirectional design. So on each side, there are solar panels for energy harvesting, UWB chip antenna for wireless ranging to localize the sensor node, and sensor probes. So in Lunar WSN, the sensor probes are used to study the electrical property of the lunar regolith, which infers the existence of water ice, and also chip antenna for wireless communication. So this configuration is make sure that no matter what the landing orientation is, it can always have RF connection with adjacent node or a central station, and it can always have sensor probe touch the lunar soil to study it, and it can always have the solar panels that face in the sunshine to harvest energy. And this is the inside of the node. It's also kind of CubeSat is stack of a PCB board. And it's modular design. So basically you can choose different modules based on what kind of data you're interested in. And in this design, I use a sensor called impedance converter. It basically can can mirror the complex impedance of the lunar regolith in a defined frequency band. So you can use that data to calculate the permittivity of the lunar soil, which infers the existence of water ice. And here's the result I did in a lab environment for the localization. And here's the result I did to measure water content in lunar soil simulant in a lab environment. You can see it can tell the difference between the lunar soil with water or without. So another project that I want to introduce in this framework is called HexSense. It's also a ballistically deployed sensor node, but it can do self-orientation. after landed on the moon. So the problem with the Lunar WSN node is, I feel like it's cool to have omnidirectional design, but the problem is, so you see on each side there's the UWB antenna for wireless ranging, and also sensor probes for studying the lunar soil. Problem with this is you need to calibrate them to use them. So that means I need to do 6 times same collaboration for each side, which is a huge amount of work. And it's only one node. So I wonder if that's possible. I can design a sensor node that can always, self-orientate itself. After landed, I can make sure that it can always have a relatively determined orientation after landed. So I can only have the one set of, radio and antenna always mounted on top. Can always have a good RF connection, no matter what. So I designed a sensor node like this. It's called Hexens. It's as big as a can of Coke. It has portion spring driven pedals, and before landed, the pedals are wrapped by fishing wire, and then when it's ready, the burning resistor will warm up and melt the fishing wire, and all the spring-driven pedal will be released and push the sensor node to stand upright. So here is one example. We did a field expedition on Svalbard, in Svalbard in July last year, and here's the one video I took there. So inside is still like this kind of modular design, a stack of PCB board, and on top of it is the LoRa module, which is used to do wireless communication with other nodes or with a central station to relay data. And for this sensor node, on each side of the sensor node, there are solar panels for energy harvesting, a burning resistor for melting the fishing wire, and there are 2 sensors. One is the optical spectrometer, and another is just temperature and humidity sensor. So sensor node is for collecting some environmental data. And but the problem is we tested on on Earth gravity. We don't know if it can successfully automatically stand up in lunar gravity. So I conducted another parabolic flight, and here's the result we got from one of the lunar problem. You can see that it successfully stand upright in a lunar gravity environment. So in the February of this year, we got opportunity to send 2 Hexens sensor nodes to the Lanzarote island, which is an lunar analog place. It has a big lava tube on the island, and because we believe that on the moon there's also lava tubes there, which could be a potential shielding for future human inhabitants. So it can protect human astronauts or other systems inside from the extreme environment on the lunar surface. So I designed 2 sensor node, Hexens node, and deployed there, one inside and one outside the lava tube to compare the data inside and outside to see if the lava tube can really provide some shielding. And on the left is the photo of the central station we use. You see the big LoRa antenna to realize the wireless communication with these 2 nodes. And on the right, 2 photos of the Hexens outside and inside the lava tube. So the Hexens is also a modular design. You can see in the middle, the orange part is the sensor payload part. So for the Lanzarote trip, I just used a very simple environmental sensor payload, which can measure CO2 level, humidity, and temperature. So on the right is the data we collected from the island. You can see the orange one is the one outside, and the blue curve is the one from the one inside. You can see that at least the environmental condition inside the lava tube is definitely much more stable than the one outside. And it's also modularly designed, so we can change the payloads based on what kind of data we are interested in. So I designed another payload, which is the custom designed 360 camera, which actually just the six cameras modules. The idea for this is we can deploy a bunch of this sensor node to an area of interest, and they can all take 360 image from different positions, different angles, and by combining the image they took and the photogrammetry, we can form a relatively more detailed 3D model of the area of interest. We can have more details, like if there are small rocks or small craters there. And this kind of information is hard to get from remote sensing from the orbit. So here's the actually six image took by this 360 camera. It's actually I stitched them together. It's actually not a very good 360 image because the camera datasheet actually claims that their FOV is it's about 67 degree, but I guess it's also up to the resolution and image format configuration. So actually it's not like a perfect 360 camera, 360 image, but I will keep working on this to make sure we can get good results. So yeah, that's all my work. It's mainly about how to use low-cost and small wireless sensor platform to facilitate future lunar and deep space exploration. So thank you. So yes,
Oh, sorry. I thought I was unmuted.
okay.
We do have a question from Keith Scott.
Oh
what
yeah,
have you,
I saw the question.
Yeah, what have you done to harden any of the electronics against radiation, or is that necessary?
Oh yeah, I saw the question. There are two. So the radiation part, actually, we consult the Lunar Outpost. Actually, they said they gave us the number of the radiation, and we didn't do radiation test. We just choose the components that most likely gonna be able to survive there. Actually, we don't have the facility to do the radiation test. We have done the TVAC test, vibration test, and shock test. That's all the the environment, the test we did. The radiation part, we just choose the components that gonna meet the requirement we need. And also inside the robot, I did some shielding to the electronics. Yeah, for the radiation part, that's all the thing I did. So the mechanism I used to recover from failure. So this actually is kind of risky mission because we only can't afford to send one robot there, and sending something to the moon is extremely expensive. To make it robust, we did a bunch of tests. For the hardware side, we just for the hardware of the AstroAnt robot design, I just I use the very common approach, like a watchdog, to make sure the robot to make sure the MCU can recover from like some abnormal failure. And from the firmware, we actually take as many abnormal scenarios into account, during the way to the moon, there might be some reboot of the rover, it might trigger the robot on by accident. So we need to handle those accident triggered on. scenario, and also on the moon. If the Bluetooth Low Energy if after the garage opened but the Bluetooth Low Energy connection cannot be built successfully, the robot, after a few minutes, the robot will automatically drive out to try to, get a better position to try to build the Bluetooth Low Energy connection built. So that's all the kind of approaches we use. Yeah.
And we have another question from Semo Grasic. First, he says, thank you for the really interesting presentation of your work. I'm curious about the wireless technologies and protocols you are currently using in your experiments.
Oh, okay. Thank you. So for the AstroAnt, I use BLE, and we built a kind of custom protocol above that, like a layer above that. We just we defined every frame is let's see, I forgot how many bytes, but with like a specific amount of bytes, and we defined the meaning of every bytes, and we defined the structure of our own frame, and we use COPS for COPS, for encoding the data, and for the wireless sensor node, I mainly use LoRa. The same thing, I use LoRa as the PHY layer, and I defined my own protocol about that. Still the same, I defined how long each frame is, and the different structure of command and data, and also what the meaning of each frame. I also use COPS for encoding the data.
Okay, so if my memory serves me correctly, you have struggled with a number of problems, through the life of your projects. One was just the kind of the lack of raw compute power, which limited you in terms of what you could do from the communication standpoint, and the others were weight. So you may have said this, but I can't remember. How much did the AstroAnt that's going to be launched end up weighing?
Like the weight of the AstroAnt?
Yeah.
Yeah. So we are responsible for the development of the AstroAnt and the central station, the little PCB. Those two combined is less than 30 grams, about 30 grams, but a little bit less than that. Yeah.
Wow. That's an amazing feat.
Yeah, I really tried my best to lower the weight and also make it as small as possible, because we really have very strict limitation on both the mass and the space we can use. So yeah, and actually I would say one of the biggest challenge is how to make it small and also as robust as possible in that harsh environment, and also to deal with a bunch of unknown scenarios that might happen. So yeah, it's really hard. For the components selection, like the motors, I really don't have that many choice. I find that maybe the only choice, maybe the only products I can use for this kind of a design. So yeah, it's quite challenging.
Yeah. Do you plan on sharing your self-orienting solution to any space agency so they can avoid embarrassments in the future? That's a joke.
Yeah, well, especially the joke actually related to me. We are taking the IM2. I already published the work, so hopefully, I really don't know how, honestly, how useful my design would be in the future. Is really not up to me if this is gonna be widely used, but I definitely hope that my design could facilitate other people's research, or the future lunar or deep space explorations in the future. So
Yeah.
yeah, hope so.
What would you say was the most difficult problem to solve that you encountered?
For both projects.
Let's say AstroAnt, the one that's going to launch. Was it the weight or something
Oh,
else?
yeah. As I mentioned, I think miniaturizing it still, and also make it as robust at the same time, is the most challenging, because I need to, for example, the to make the I think like a lot of a space system, they have a very complex thermal system,
Mhm.
to deal with low and high temperature. But the thermal system normally is something like a liquid carbon dioxide loop. Can take the heat, but I can also heat things up. Um, but they are all very bulky and very complicated, and such tiny robot is impossible. At least currently, it's impossible to have that complex thermal system. So I need to do some trade-off, because we are going to the Lunar South Pole, and the incident angle of the sunshine is actually not that good for heating things up. You will just heat things from the side, and that means on the surface is actually we won't get that much heat. So I decide like dealing with the low temperature is more important,
Mhm.
especially when it's too cold. When it's too cold, it's bad for it's bad to charge the battery in low temperature, because this will just destroy the temperature, the battery. And I'm sorry, I would be bad to charge the battery in low temperature. And when the temperature is too low, it will also lower the output voltage of the battery, because the internal resistance will get very high. So that's why I use a tiny heater attached to the battery to warm it up.
Mm.
So there's a lot of trade-offs during the development. So we need to deal with, because we have limited mass, and the robot has limited capability. So we still need to make sure that it can be as capable and as robust as possible. And that's from the technical part. I think another very challenging part for myself is the collaboration part, because students in my group, um, we are more like system engineer. You see, all this project actually, I basically designed and made everything from the mechanical design to the electronics to the firmware to the software and to all the test plan. I did everything. But in the AstroAnt project, we need to collaborate closely with the Lunar Outpost, because everything gonna be working on their rover, and they also have a bunch of requirements, and we also have a lot of wishful thinking. So sometimes we need to like negotiate to get the balance point, which makes both of us happy. And also during the development and also the collaboration with them, one very important thing I found is to clarify every detail, even though it's something you thought is common sense that everybody knows what it means. But sometimes you really need to clarify everything to make sure everybody is on the same page, has exactly the same understanding of every word. Um, Sometimes this really matters. So actually, this is kind of quite challenging for me. Yeah, I guess for the AstroAnt, this is two most challenging part for me.
Okay. And just a couple of final questions.
Yeah.
Do you have a kind of a firm launch date yet?
Not really. I went to the IEEE Aerospace conference at the beginning of this year, and I met some guys from Intuitive Machine, and they didn't tell me anything.
Uh,
Yeah.
okay.
Yes.
And finally, how long do you expect AstroAnt to remain operational?
Good question. Actually, in the lab environment, I tested it will keep working for about 8 hours with both motor, like they keep moving and with wireless communication on. But on the moon, I guess it will be much shorter than this, maybe just a few hours.
Hmm.
Yeah, this is one time mission. After the garage opened and the AstroAnt finished charging, it's on its own. This is also kind of a big trade-off I did. At the very beginning, I was about to add a small solar cell to it. But as we have really limited space inside, you can see it has many things inside. We really don't have any space for the solar energy charger. The solar panel actually is no problem. I think I can make it, but the solar energy charger sometimes they need big components like big inductors, and I really don't have the space for them. So I just decided, oh, it's just gonna be one charge and one time thing. Yeah.
Okay. Well, thanks very much for a fascinating presentation, and
Thank you.
we'll drop you a note, let you know when the video's available online, and please send us your presentation materials so we can post those also on our events page for people that might be interested in them. So this concludes our event. Remember, you can get information about upcoming and past events at our events page, which is ipnsig.org/events. And that's where you can also get links to video recordings and presentation materials. And then because we're crassly commercial, no, we're nonprofit, which means we're poor and we need donations. Please feel free to donate to IPNSIG.org. We are a 501c3 organization under the U.S. Internal Revenue Service. Next slide. And become a member of IPNSIG. It's free. There's a membership link on the webpage, and we truly are a global organization, one of only two chapters within ISOC that have global versus regional members. And once again, I want to thank you for your attendance and attention and questions. And just a reminder that when you exit, you'll be redirected to a short survey. Please take a moment and fill that out. So thanks again, Fangjing, and good luck with your project and keep us posted.
Thank you. Thank you, Mike. Thanks, everyone.
Thank you. So long. This concludes the festivities. The mass has ended. We can go in peace.